Hey guys, we're going to pick up where we left off. Question number 7 of diagnostic test, and we're only going to go up to 15. So certain car manufacturers installed a gauge to tell drivers how many miles they can drive until they run out of gas. So let's set up our formula. So if we look at this information here, we can write a formula. Y hat, or what we're predicting will happen, is equal to, and this is our constant. So constants don't have, are numbers that don't change, right? So a constant, that's our y-intercept, plus that's our slope, right? Times the gauge. So that's how much the gauge is changing. Okay, so we write it like this, and this is our x value in our equation, and this is our y. So how do I figure out which one is which? Both of them are miles, so this is a little tricky. Well, we see here that it's distance versus the gauge reading. So since the word gauge is here, I know that's x. So this is my equation, and this one then would have to be y, distance traveled. So let's take a look. It says identify and interpret the slope. So we know that this is the slope. That's where the slope always is in the printout. So we've narrowed it down to A and D. Now what's different between these two, and why does D not work? Well, see this word predicted. That's this hat thing, right? So what is slope? Well, slope is the change of y over the change of x, but it's the change of the prediction. So we would predict that that's how much the distance would change. So we could go an additional 1.19 miles. You could drive that many more miles for every mile that's on the gauge. So it looks like the gauge is relatively conservative. You can actually drive a little bit further on that 1 mile on the gauge because we don't want people running out of gas. So that means that A has to be our answer. Okay, let's take a look at the next one. On question number 8, a well-balanced stock portfolio would have an equation like this, where this is the amount that was originally invested in, and T is in months. Okay, so we got to be careful with that. So it says, using this equation, what's the predicted balanced portfolio in months? So you might be thinking, well, hold on a minute. I thought this class only went up to Algebra 2, and when I see this natural log business, LN, I'm thinking pre-calculus. Okay, well, you're right. This is likely not on the test because I usually get into this information in Unit 9, and they chopped off Unit 9. But technically, I could have gone over it back in Chapter 3. So it still might be on the test. So let's go through how you do this. If I have to put this in months, then I'm just going to use this equation given, and I'm going to step through the algebra steps. So I rewrite my equation, and then I'm going to plug in 24 for T because that's how much time has gone by. So when I do that and I plug in 24 for T, I end up getting the answer. The natural log of balance, my predicted balance in my portfolio would be about 7. Now you're saying to yourself, well, why isn't that my answer, B? Well, the problem is you didn't get the variable by itself on one side. We're trying to solve for the predicted balance. What is the predicted balance? And it is not by itself on one side. So in order to get it by itself on one side, you have to use the inverse operation to both sides because that's an equal sign. So what I need to do right now is I need to take e to the power of both sides so that I can undo that natural log. So I've done that here. If I take e to the power of all this stuff and e to the power of all that stuff, it should, the left side of the equation should still equal the right side of the equation. Okay. Well, now, why would I have done that? Well, these are inverse operations, and you might say to yourself, well, how would I know that? Well, your trusty calculator here shows you inverse operations. Notice here, the inverse of squaring something is square rooting. That's how you get rid of a square root sign. You square stuff. How do you get rid of a log? You take something both sides to the power of 10. How do you get rid of power to the 10? You take the log. Those are inverse. Same with e to the power and the natural log. They're inverse operations. You might be thinking, I don't even know what you're talking about, this inverse operation stuff. Well, those have existed for all time, even since kindergarten. Instead of adding, we subtract, or we subtract instead of add. That undoes what we did. And same with multiply and divide. Those are inverse operations as well. Okay, so once I do that, e to the power of the natural log of the balance would just give me the predicted balance, and I finally have that on one side by itself. So when I take e to the power, you might go, I don't even know how to do that. Well, hold on to your horses. Here we go. When I go to a calculator, I take e, and there it is, e to the power of 6.798. Okay, enter, there it is. There's my answer. But remember that the problem said that's my answer in thousands of dollars. So that's why my answer is D. All right, next question. At this high school, we surveyed 28 freshmen, 26 sophomores, 24 juniors, and 22 seniors. This is called a stratification. So hopefully you chose D. But you're watching the video, so that means you didn't. So let's talk. It's definitely not a simple random sample because every person did not have an equal chance of being chosen, okay? If you did, then you just would have taken 100 students in the total school, and that maybe would have given you different percentages across the board. You just picked 100 kids at the school. End of story. This is a stratified random sample. Just because I'm picking from different groups, this number doesn't have to be the same. If you thought it could have been a cluster sample, let me explain what that is. So a cluster sample would be if we took a whole clump. So imagine if we wanted to sample, not the entire school, just a clump. But we wanted to get everybody. We wanted to get freshmen, sophomores, juniors, seniors. We wanted to get kids in all the programs, maybe kids from all over the school. So if we surveyed everyone in building 1 on a Wednesday morning, we would get some of every grade level and some of everybody from every background, and that would be called a clump or a cluster random sample. We survey everybody in that clump. Okay. Question number 10. We did a study to investigate whether the customers are satisfied. This is not an experiment because there was no treatment. We just observed after the fact. So what makes it stratified? If you notice here, we had 2 distinct populations. There were ones that purchased computers that offered tech support and ones that purchased computers without tech support. So those are specifically 2 groups that may have different opinions based on their groups. That's similar to this. Based on how long you've been in high school, you may have different opinions based on your group. Okay. All right, so what is this stuff? This is for the next question. So let's take a look. Toddlers have a tendency to have an abundance of energy. So a fitness instructor decided to make a class, and she got 40 volunteers. The real kicker in this problem is the word volunteer and the idea that whenever you're using humans, you can't put a gun to their head, right? That is not legal in our country. You can't force people to be in an experiment. So what is the treatment? Well, the treatment is you did the fitness class and everybody did that fitness class. Okay. So once the class ended, the instructor learned the mean number of calories burned by the participants was significantly greater than the ones burned by participants in a standard class. So you'd like to say, oh, I'd love to say there is convincing evidence that it caused them to burn more calories. But many of us are hesitant to say the word caused. So you might be going back and forth. Do I say caused or is that too strong? And I have to say there's an association. Well, the answer to that question is this. We can say cause and effect in an experiment, but we must be careful about who we make an inference about. Okay, what does that mean? I'm gonna try to explain that. What that means is that Imagine another scenario. Imagine I took 20 volunteers out of my 150 geometry students and gave them an extra review class. They volunteered for this extra review class. I didn't force them to. It was extra. So let's say that everybody in my extra review class, their grade went up 2 letter grades. They did that much better when we retook the test. I'd love to be able to say that my review session caused the increase in the retest. However, there could be something other. There could be another characteristic at play that's making the scores go up. Maybe after they left the review course, because they are just kind of an outgoing student that's trying to do everything possible, maybe they ended up studying more, and that's what caused it to go up. Or maybe they got they met somebody in the review class, and then they went to Panera afterward and studied, and that's why their score went up. So I can only make an inference about the 20 people. I can use cause and effect, but I can only use it for the 20 kids that were in that class, okay? Only for the group of people. So if I had 20 volunteers and half of them did the review class and half of them didn't, and the people that were in the review class, they definitely went up, then I can only make an inference about the volunteers. I can't extend past that. And that's why I chose C. All right. Let's keep going. I think I can do the rest on one tape, so let's do it. 12. In order to examine the proportion of students that text while driving, an administrator selected a random sample and asked them questions. What's going on here? Well, since it's a very face-to-face meeting and the fear of authority, that's going to be called response bias. So I've told you this story all year. In years past, we did an experiment where one of my students was wearing glasses at Chipotle, and she asked randomly her customers if they feel glasses are more attractive. And if you ask that question while wearing glasses, then that's called response bias, because people just don't want to be rude. So they might just try to be agreeable, and they notice, oh, you're wearing glasses. So yeah, it makes you look smart, right? Do glasses make you look more attractive, or do glasses make you look more smart? Because you're wearing glasses, that's throwing off their response, and that's called response bias. Okay, next one, 13. Let's take a look. There's 2 ways we could have done this. So let's see. Let's assume there were just 100 kids in school, which you're 1,000 kids or 100, but then you're going to have a half of a kid. But so it says AP Stats had 48 and a half students. Okay, so 48 and a half students in AP Stats. Remember, I put this in parentheses because that's not how many, that's how many are in this circle, but that's not where people are standing. Then I also know that 52 are in AP Calc, 52.5. So if it was actual people, 52 and a half people are taking AP Calc, and that's the total number of people in this circle. So why isn't it a real number outside of a parentheses? That's because I don't know about this overlap. I don't want to count them twice. So let's figure out what's happening in the overlap. It says 10% took both. So that means 10 kids took both. So now we know that only 38 and a half took stats out of 100, and only 52.5 took calc out of 100. Ooh, 42 and a half, sorry. Right? Because 10 are both, and we don't want to count those both. Okay, so hopefully that helps make sense. And you can use decimals, and then all the decimals need to add up to 1. Or you can turn them into amount of people out of 100, and you can also do that. Same type of thing. So now what's happening here? Well, these are actually students standing in these circles. So when we add up these numbers, or if we add up the decimals like I did, right? You can add up these decimals. I get 0.91, or I get 91 kids. So 91 kids are spoken for. That means 9 kids are not taking either of these classes at all. None of those classes. They're not taking that. They're not taking that. Maybe they're going to SPC. Who knows? Maybe they're graduating early. These were juniors in pre-calc. So that's the question, is what's the probability that you're not taking either one? And then that's 9%. I'm going to stop the video there. Let's keep going. All right, question number 14. An online clothing company decides to investigate whether their customers have a coupon. So we asked them 2 questions. Do you have a coupon? And then did you make a second purchase within the next 30 days? So we're being asked, based on this, are they independent? So the test for independent means the 2 events are independent if the probability of A is equal to the probability of A given B. So let's look at that. The probability of A, if you made a second purchase, it looks like 50 people said, yes, I made a second purchase. Okay, so that's the probability of A. What is the probability of B? It says B is, yes, I got sent a coupon. So 60% of people got sent a coupon. So how do I calculate this, the probability of A given B? Well, it's given B. So given that you got sent a coupon. So these are the people that got sent a coupon. And 34 of those are A out of the 60. So when I look at these, I notice they're not equal to each other. So that's why I choose C. I know that is not independent because they are not equal to each other. Okay, last question. Love this one. It says you can't please everybody. Don't we know it? So how do I answer this question, and how do I know that it's a binomial distribution? Well, this is the test, bits. So let's walk it through. They either let people say, yes, I'm displeased, or no, I am not displeased. So it's definitely binary. You only have 2 choices. Looks to be independent. We know how many trials because we only asked 25 people. And then what is the probability of success, and is it the complement of failure? And we see that it is. So we know the probability of success is 0.045, and that would mean the probability of failure or not being displeased would be 0.955. Now, because it fits the test for binomial distribution, we can do this on our calculator. So if you want to pause the video and kind of write that out, and I'm going to show you the steps. So I go to Stats, Distribution, and I scroll all the way down to Binomial CDF. Okay, so the number of trials is 25. The probability of yes, I'm displeased is 0.0545. And they said, what's the probability at least 2 were displeased? So 2 would be at least 2, and 3 would be at least 2. So all the way up to 25. So my lower bound is 2, and my upper bound is 25. Bada boom, bada bing. There's my answer, guys. Thanks for joining us.